Hey everyone. Okay, so in lesson 4, we're going to turn our attention to curve sketching. Now, we've already done curve sketching, so the process of what we're about to do is the exact same as the whole unit we just did, okay? The difference is in the curve sketching unit that we did, we dealt primarily with rational functions, with polynomial functions, a little bit of radical functions in there. So now essentially we're just going to take those thoughts and apply them to trig graphs, okay? Just like in the next unit, when we do exponents and logs, we will have a day of curve sketching where now we're gonna curve sketch exponents and logs. Today, we're gonna focus on curve sketching various trig graphs, okay? So you will recall these steps that I've given you as far as the analysis go. They are the same steps. The procedure remains exactly the same. So we're going to figure out the domain. Then we're going to determine the zeros, the x-intercepts and the y-intercepts. We're going to take a look at any asymptotes. We're going to use the first derivative test to determine whether the function is increasing or decreasing. Then we'll take a look at the second derivative or the first derivative test to determine relative extrema, so local max and mins. The second derivative will also talk to us about possible points of inflection as well as concavity. And then we're going to put all that together into a nice, well-sketched, well-labeled, well-curved drawing, okay? All right, so the one we're going to do today together is y equals cos of x minus sine of x, and we're going to do it on the interval negative pi to pi. So that means we're not going to have this this domain going forever. We're only going to look at it from negative pi to pi. So domain, we just said it, it's going to be from negative pi to pi, okay? Those should be square brackets because I can equal negative pi and I can equal pi, okay? So let's just change that to square brackets like that. Okay, now we want to take a look at x-intercepts and y-intercepts. If I want to do the y-intercept, I'm going to plug 0 in for x. I know cos of 0 is 1 and sine of 0 is 0, so that ends up being 1. So I know I have a y-intercept at 0, 1. For x-intercepts, I'm going to plug 0 in for y and solve for x. So I'm looking at 0 equals cos of x minus sine of x. I'm going to bring the sine of x over. So I'm looking for where sine of x equals cos of x. I know that that happens in quadrant 1 at pi over 4. And I know that it happens in quadrant 3 at 5 pi over 4. Now, 5 pi over 4 is outside of my domain, but the negative version of 5 pi over 4 is not. The negative version of 5 pi over 4 would be negative 3 pi over 4. So I know I have intercepts at pi over 4, 0, and negative 3 pi over 4, 0. Okay. Okay, then we take a look at asymptotes in a trig graph. There is none for this particular trig graph, okay? If I ended up with a trig graph that had a fraction of some sort there, there's a possibility of asymptotes. There's also a possibility of, like, even if I just gave you secant, you know that secant's 1 over cosine, so you're going to have some sort of an asymptote there as well, okay? But for this guy, we're just dealing with cosine and sine, so there's no asymptotes, okay? So now we want to take a look at intervals of increasing and decreasing. Well, to do that, I need to take the derivative, okay? So I'm looking at the derivative of cos is negative sine, and then minus the derivative of sine is cos. So I end up with negative sine minus cos. Okay, and to get the intervals of increasing or decreasing, we set the derivative, first derivative, equal to 0 or equal to not existing. There is no spot here where it wouldn't exist. So I just set it equal to 0. I'm looking for when cos of x will equal negative sine of x. So when are they the opposite signs? That actually is going to be still my pi over 4 reference, but we're going to be looking in quadrants 2 and in quadrants 4. Okay, so in quadrant 2, I'd be 3 pi over 4. In quadrant 4, I'd be essentially negative pi over 4 with respect to the domain that I'm given right now. So negative pi over 4 and 3 pi over 4. I'm going to put those on a number line. I'm going to check to the left, in between, and to the right, and see what's positive and what's negative. Okay, I want you to also notice I stuck my endpoints there, and the reason, oh, I might be in the way. Let me just get my head out of the way there. I stuck my endpoints there, and the reason I stuck my endpoints there is because I want to make sure the number I choose doesn't go beyond the endpoint, right? Because that could screw things up. So the number I'm putting here, I need to make sure it's somewhere in between negative pi and negative pi over 4, okay? Okay, so I assume you're pausing as we go through this and you're trying these things yourself, so I'm going to keep plugging along. End up with positive and negative and positive. Okay, so I know I'm increasing from negative pi to negative pi over 4 in union with 3 pi over 4 to pi. Again, remember that we have specific endpoints here, so I can't say negative infinity to negative pi over 4. Okay, and then I'm decreasing from negative pi over 4 to 3 pi over 4. Okay, so now I also want to talk about local max or mins. I am at negative pi over 4, switching from increasing to decreasing, so that's a local maximum. And at 3 pi over 4, I'm switching from decreasing to increasing, so that would be a local minimum. So I need to plug negative pi over 4 back into my original equation, get the y value. I need to plug 3 pi over 4 back into my original equation, get the y value, and then state those as my local max and mins. Okay, so I have a local max at negative pi over 4, comma, root 2, and I have a local min at 3 pi over 4, comma, negative root 2. Okay. All right. Now, I also have endpoints here of negative pi, comma, negative 1, and pi, comma, negative 1. Okay, I'm going to include that in this conversation because I want to make sure I accurately plot those. Okay. So that's 1, 2, 3, 4 points to plot, as well as the 3 intercepts that we've already plotted. So far I have 7 points that have to be plotted accurately. So now we want to talk about concavity and points of inflection. We've already discussed that the first derivative was negative sine x minus cos x. So now I need to get the second derivative. So I'm going to take the derivative of the first derivative. The derivative of sine is cos, so that'll be negative cos. The derivative of cos is negative sine, so that's going to end up being plus sine x. So negative cos x plus sine x, or sine x minus cos x. Okay. To get the points I want to be thinking of, I want to set the second derivative equal to 0 or non-existent. I can't be non-existent in this particular one. Okay, and so again, I'm looking for spots where cos of x and sine of x are the same thing. And again, that would be actually at my intercepts. We've already figured those out, right? And my x-intercepts, negative 3 pi over 4 and pi over 4. Okay, but I want to put those on a number line and test them. Remember, when I'm testing them now, I'm plugging these points into the second derivative to see whether the second derivative is positive or negative. Okay, you always want to make sure you're not getting lost as to where you're plugging in the numbers. Okay, so when I plug that in, I should get positive, negative, positive. So I do see a changing concavity at negative 3 pi over 4, and I see a changing concavity at pi over 4. Okay, so I'm going to say I'm concaving up from negative pi to negative 3 pi over 4 in union with pi over 4 to pi, and I'm concaving down from negative 3 pi over 4 to pi over 4. That also tells me I have points of inflection at negative 3 pi over 4 and pi over 4. So I want to state that as well. Okay, so points of inflection at negative 3 pi over 4, comma 0 and pi over 4, comma 0. Now in this instance, that doesn't give us additional points. Those are points we've already discussed. Okay. All right. And now we get to graph. Those of you who had me in 30-1 know that I'm very particular about how you draw sine graphs and cosine graphs. I need to see a nice curve. I do not want these to be a series of straight segments. I need to see that point of inflection. I need to see how you're changing concavity there. So I need to see that it's going from concaving down to concaving up, okay? All right, so a good graph is gonna look something like this, okay? You will note that I've labeled all the points that I discussed. And here's where we're looking for that change in concavity, okay? So I'm going from a curve that way to kind of a curve that way. You want to kind of see that bend in there, okay? You want these nice rounded edges on the top and on the bottom, okay? I don't want this to come up to like, I find lots of kids invert this, like they're gonna go something like this almost. Now I'm exaggerating that, but I don't want that, okay? It's gonna be a nice rounded curve. Okay. All right. So that's what you're doing today. It's going to feel really familiar, I think. I think you're going to have a good time with it. But as always, if you do have questions, please don't let your questions go unasked. Make sure you come and see me. Okay. So here is your homework. And then next up for us will be starting a couple of days of applications. I've broken applications down into a part 1 and a part 2. Okay. See you there. Bye.